Okay, today we're going to talk about the limit and what that is in mathematics. This is section 1.1 that we're covering today. And we'll probably we'll be able to finish 1.1 and start section 1.2 today. But for now, we're talking about the limit of a function as x approaches a certain point. And the best way to talk about this is with an example. The actual definition is kind of a little complicated and technical, so I'm going to start with an example and then we'll work from there to get to the definition of a limit. So my example is the function f of x equal x squared minus 4 over x minus 2. And let's say that we're interested in function values around the point x equal 2. First, you'll notice that if I evaluate it at x equal 2, my function value, when I plug in 2, is undefined. And that's because I get 4. 2 squared is 4 minus 4. 0 in the numerator is okay, but notice we have 2 minus 2, and that gives me 0 in the denominator. We cannot divide by 0. So in this case, f of 2 is undefined. Okay, so we know that it's undefined at 2, but what is happening around 2 or very close to 2? And the best way to analyze this is to go ahead and look at values around 2, like plugging them into a table. So I'm going to draw a table here. We've got x values, which are the input, the y values are the output, and those are the function values, okay? So let's pick numbers around 2. And I'm going to start on the negative side of 2. So less than 2, 1.9. And then even closer to 2, 1.99. And yet again, even closer, 1.999. Okay, these are the input values. What are the output values? And if you do the calculation, I did this ahead of time. What I'm doing is I'm taking 1.9 and plugging it in here for x. And then I calculate what I get. And the output for 1.9 is 3.9. If I put in 1.99, the output is 3.99. And if I put in 1.999, the output is 3.999. So you can see a pattern here. As x gets closer to 2, the y values are getting closer and closer to 4. And the way we write this in mathematics is we say the limit as x approaches 2, and I'm going to put a little negative sign here to show that I'm coming from the negative side of 2. So in other words, these values are less than 2, so that's what that negative there means. And the function that I'm looking at, of course, comes next. That's the x squared minus 4 over x minus 2. So as x gets close to 2 from the negative side, the function is going to get close to 4. So we say the limit as x approaches 2 from the negative side of our function equals 4. Okay? Now we can do the same thing from the positive side. So something that's a little bit greater than 2, I'm plugging that in. And then closer to 2 would be something like 2.01. Even closer is 2.001. And when I plug in those values, I get 4.1 for the output, 4.01 when I plug this 2.01 in, and 4.001. Okay, so Same thing. The difference is if I'm looking at these values here, I'm on the positive side of 2. So I'm going to write that as the limit as x approaches 2 from the positive side of our function. That's also 4. Okay, so that's the notion of a limit. And because they're coming closer and closer to 4 from both sides, in general, we say, the way we word this is we say the limit as x approaches 2 of our function of f of x, and our function is x squared minus 4 over x minus 2 in this example, is 4. So the limit is 4. And this brings us to the point that the limit is a y value, okay? It's important to remind yourself of that. Whoops, sorry. The limit value is a y value. And mathematically, so this is in English right here, sort of. The limit as x approaches 2 of f of x is 4. The way we write that in math language is we say the limit as x approaches 2 of our function equals 4. Now, so let's look at the 3 situations. Here we have the left-hand limit because of that little negative sign there. Here we have the right-hand limit because of that little positive sign there. So notice down here, I didn't have any sign. I left it blank after the 2 there. That just means we're talking about both sides, okay? Both sides of the x values, which is 2 in this case, both sides of 2. Okay, so in order for the limit to exist, both the left-hand limit and the right-hand limit must exist, and they have to be equal to each other. So let me write that over here. Okay, this is a very important point. So let me repeat it. In order for the limit to exist, that's this limit here. In order for it to exist, both the left-hand limit, that's up here, and the right-hand limit must exist, and they have to be equal to each other. So in this example, the limit does exist, and we have it equal to 4. Okay, so that's so this is the conclusion of our example. Now I want to kind of formalize a little bit what how that works. So I'm going to let you finish writing there for a minute. And then I'm going to continue. Remember, I'm recording all of these lectures, so if your notes are incomplete in any way, you can always go back and fill in the details. So in general, or generally, in order for a function f of x to have a limit L, as x values approach a constant a, the left-hand limit and the right-hand limit must be equal the left-hand limit and the right-hand limit must be equal. I should say must exist and be equal. And so in other words, the limit as x approaches a from the negative side of f of x equals the limit as x approaches a from the positive side of f of x, and they're both equal to some constant L. The fact that they're equal to a constant L means they exist and they are equal. So if this is true, we say that the limit as x approaches a from either side, so that's why this is blank here, of f of x equals L. So for the purpose of determining if a function has a limit, we look at the left hand and the right hand limits, and then if they're equal, then we can say in general the limit is equal to L. Okay. I'm kind of talking here, and there's someone else, a professor in another room, and my door's open. So give me a moment while you're copying this down. I'm going to go shut the door in the classroom. And I'm going to try and focus it in better. Okay. Remember now, you can unmute yourself at any point and chime in if you have a question or if you want to make a comment. I value that interaction. So, okay, so let's look at some examples that are graphs that will kind of help solidify these concepts, because this is kind of abstract, right? And I think if you see a picture, it'll make more sense for you. So that's what I'm going to do now. I'm going to look at some examples. Okay, so we're looking in the rectangular coordinate system. And I have a random function here. We'll call it f. And let's consider the limit values around a certain point. Let's say a is there. So if I want to see what is happening at A, I draw a vertical line until I reach my graph. And then from that point on the graph, I draw a horizontal line over, okay? That is going to be where my limit is. So x is getting close to a, then when we put that through the function, our function values are getting close to L, okay, right around this general area. So remember, function values are y values. So we're talking about the height or the level here. And you can see things are getting closer and closer to this level L as the x values, which are the input, get close to a, okay? So in this particular example, we say that the limit as x approaches a of our function f of x is equal to L. And notice that f of a, so if you're exactly at a, we go through the function, you're going to be exactly at L. So for this particular example, f of a is equal to L. All right. All right, so now I'm going to draw a function that's a little different. It's a curve, but then it has a hole right there. And at that spot, the x value is a, and the y value is L. Okay, so it's really close, similar to this example. The difference is we have a hole there, but we can still say that the limit as x approaches a of f of x is equal to L, but we cannot say that f of a equals L. F of a is actually undefined. And this part is because there's a hole there. So if I plug in a, the function doesn't exist there, right? So the output is undefined. But the height where that occurs is at L. So around that open circle, it's getting closer and closer to L, the function values or the output around that circle. So as x gets close to a, the function values get close to L. And that's what we mean by limit. The limits are always referring to around a certain point as you get close to it. But for this particular function at a, it's undefined. Okay? Any questions on that? Okay, so let's look at example 3 now. Okay, so here we have a function similar to example 2. It has a hole. Let's say like that. And we'll call this f, call this f over here. Okay, so now it's going to have a function value at a. So here's my a value. Actually, it's on the x-axis, so I'll just put it like that. And the limit value is L. And then we have another value here. We'll call that b, okay? So in this particular example, if you are at a, right here at a, we hit the function right here. It doesn't exist up here, but there's a point right here that is in the function, the collection of ordered pairs that make up the function. And so the output is the b here. But the limit values, so as you get close to a, when you put your x value into the function, it's going to be close to L, the output is. And if on this side, if you get close to a and you go through the function, you're going to be close to L. So the way we write that is we say the limit as x approaches a of f of x equals L, but f of a, it exists, but it's equal to b. So the values, the limit values are different than the function value, okay? The limit values are close to L, whereas the function value is equal to B. So that's a third situation that you might run into. All right, finally, here we have a function that has a break in the graph. So you'll notice that as we get close to A, on the left-hand side, we're getting close to this height here. Let's call that height B, and up here we'll call this height A. Okay. So as we come on the left here, as we get close to A from the left-hand side, we're coming into A, and we go to the function, they're going to be close to B. On the other side, if we come in to get close to A and we go to the function, we're going to be up close to A. So there's a disparity there for the limits, the left-hand limit and the right-hand limit. And remember earlier I said, in order for a limit to exist at a point, both the left-hand limit and the right-hand limit must exist, and they have to be equal. But in this example, we can see the left-hand limit is equal to B and the right-hand limit is equal to A. So let me write that. Let me get a different color here. I got too much purple. So the limit as x approaches A, and I probably should have used a different letter here. This is A, this is a different A. Let me call this C, actually. That's better. So the limit as x approaches A, so here we are on the x-axis, from the left-hand side, now I'm going to put a little negative there, for my function f of x, that's going to equal B, okay? Whereas the limit as x approaches A on the positive side for our function is going to equal C. I'm kind of crowded in here. I'm trying to separate all this out. Okay. So this means the limit as x approaches A of f of x does not exist. And sometimes you'll see people write D, N, E. It's just a shorthand because in mathematics, we run into that situation a lot where something does not exist. So we just get in the habit of writing D, N, E. So if you see it written like this, you'll know what that means. Okay. Now, what about the function value? Can anybody tell me what the function value is at A? Does anybody want to give a shot? Unmute and give me a shot at that one. What is the function value at A? In other words, f of A. What do you get when you plug in A? Anybody out there want to give that a shot? Okay. So here we are. A is the input. Notice we have to pass through our function because this is an open circle. The function does not exist there. But if we continue drawing our vertical line, we hit the graph right there. And so the output is going to be C. So f of A equals C. Okay. So those are some examples to help you kind of get a feel for how this works. It is possible for the function value to not exist, but the limit to exist. And that's just simply because the limit is around a point, whereas the function value is at a point. And so we're really looking at different locations when we're talking about limits versus function values. Okay, and these, it's kind of conceptually a little tricky, but the best thing is to practice these. There are quite a few of these homework problems, so just get a lot of practice. The problems are quick to solve, but they're conceptually difficult, so you may have to take a few shots to get the answer right. But you really want to understand what's going on with limits. Okay, let me check my notes here. I want to talk briefly about limits of infinity. Limits of infinity are not a topic that we're going to spend a lot of time in. I'm just going to do one example and discuss it briefly because it's not something you're going to run into this class very much at all. In the real world, we don't deal with infinity very much. In the context of business applications, you're looking for a number, right? A bottom line, basically. So we're not going to be dealing with a lot of limits of infinity, but I'm just going to do one example just so I can say that we covered that and you'll know how to do the homework problems. So example, just like we did with in the previous, an example is the best way to study this. So I'm going to look at the example, f of x equals 2 over x plus 3. And this one's a little bit different than our original example. Notice that if I plug in -3, I'm going to get 2 divided by -3 plus 3. And that becomes 2 divided by 0. This is undefined. So that was just like in our first example. Let me go back to that first example for a minute here. Recall that when I plugged in 2, I got 0 divided by 0. That's a special case where you still have a limit, but the function value doesn't exist. In this particular example, we don't have 0 divided by 0, we have 2 divided by 0. So what happens is when you get close to -3, you're going to get very small numbers, but your numerator is a constant. So a constant divided by a very, very small number is actually a huge number. And that's where we get our limits of infinity. So let's go ahead and draw a table and plug in some values so we can see what's happening here. So my input is x, my output is y, and those of course are function values. The output values are function values. And I want to pick numbers that are close to -3. So I'm going to pick -3.1, let's say. And this is on the negative side. It's more negative than -3. And then -3.01, that's even closer to -3 on the negative side, and -3.001. When I plug these numbers into my function here, I'm going to get the values of -20, -200, -2000. You can kind of see the pattern here. As I get closer and closer to 3 from the negative side, my numbers are getting very large, largely negative, okay? So this is going to just this trend is going to keep going on. So you can see it's kind of expanding without bound in the negative direction, okay? And the way I would write that, I would say that the limit as x approaches -3 and from the negative side. So if I draw a number line, let's see, where can I do that? I'll do that right here. I'm focused at -3, but these numbers are on the left side. So I'm just going to write that here. And the left side is also called the negative side. Doesn't mean that, I mean, we have some negative numbers over here, right? -2, -1, but -2 and -1 are on the positive side of -3. And so this side is the right side of -3, and we call that the positive side. Okay, so back to my limit here. The limit as x approaches -3 from the negative side for my function f of x, and in this example, it's 2 over x plus 3, it's going to equal -infinity. Now, I want to be careful and mention that -infinity, nothing can be equal to -infinity, right? This is just a notation that means the limit has no bound. It's going down very negatively, and the numbers are getting larger and larger. Just like this trend here, the numbers are getting larger and larger, and they're all negative. So this is just a notation. You can't say that anything is really equal to -infinity. So I just want to clarify that. It's just to show that they're increasing negatively without bound. Okay, so looking now at the right-hand side, of -3. The numbers that I picked are -2.9. That's pretty close to -3. -2.99 is even closer. And -2.999 is yet again even closer. When I plug in those numbers, the output values, so I'm taking these numbers and I'm putting them in here for x, and then I'm calculating this function value. Those numbers are 20, 200, and 2,000. Okay, so the way I can interpret this is the limit as x gets closer to -3 from the positive side now for our function f of x is +infinity. And again, it can't be equal to infinity, but we just use that as a description of the fact that these numbers here are increasing without bound, and they're increasing positively. So these are the negative numbers. That's why we have the -infinity. These are positive. That's why we have the +infinity. So basically, because these are infinite, the limit as x approaches -3 for our function f of x does not exist. And let me reiterate, these limits also do not exist. In order for a limit to exist, it has to be a constant. It can't be infinity. You can't have a limit on something that's infinite, right? There's no limit there. Okay, so I just want to clarify that. Any questions on this? So this is, let me just look at the graph of this or show you the graph of this to help you kind of get visually what's going on, because sometimes this is a little bit abstract or too abstract to really understand. So let me just draw the graph real quick. Again, if I'm going too fast, just take some time to go back to your notes to fill in the details if you need to, because I'm going to be posting this recording later. Okay, so the function that I'm still looking at is the same example. So if I want to graph this in the rectangular coordinate system, our focal point, remember, is -3. And at -3, the function is undefined because division by 0 is not allowed. So I'm going to draw an asymptote. That's kind of just showing me that the function cannot exist there. But if I get close to -3 on the left side, these numbers are going off to -infinity. Now these are output values. So these are, oh, I'm not right here. These are output values. The function is going off to -infinity. Okay, so on my graph, what that looks like, remember, function values are y values. So it's the y values that are going down. So as we get closer and closer to -3, our y values are going down like that. And similarly, on the right-hand side, as we get closer and closer to -3, our function values go off to +infinity. This is called a hyperbola. Okay, and I didn't plug in these numbers correctly, so that might be off a little bit, but I'm just trying to give you a general picture of what it looks like. It's a hyperbola, and there's this divergence here at -3. So on the left, the function values go down to -infinity, and on the right, they go to +infinity. What happens if you're looking at x values that are very negative? So let's look at that situation. So in that case, we're saying the limit as x approaches infinity of our function, 2 over x plus 3, or f of x, what is that equal to? Well, now we're kind of looking at a different aspect. We're looking at x going off to +infinity. So that would be heading off in this direction. The x values are going this way. What are happening to the y values? They're getting closer and closer to this level right here. What is that level? This x-axis is at a level of 0. Y is 0 on the x-axis. And these values, the level of this function, is getting closer and closer to the x-axis. So that means the limit, it never reaches the x-axis, but it gets closer and closer. So the limit is 0. All right. And similarly, if we are coming from, if x is approaching -infinity of our function, 2 over x plus 3, we're going off this way. Okay. So it gets closer and closer to the x-axis, but never reaches. So the limit is at that level of the x-axis, and the y value on the x-axis is 0. Remember, limit values are y values. So you're always going to be asking yourself, what's happening to the function or the y values when I go off in a certain direction, or if I get close to a point? So if I get close to -3, the y values are going off to -infinity and +infinity. But if x gets way out here to infinity, -infinity, the y values are getting close to 0. And here on the right, the y values are getting close to 0. So the limit values are y values. Okay, always remind yourself of that note. Limit values are y values. Okay, so this is the x values and these are the y values. Any questions? Anybody want to interrupt me and say, hey, I don't understand, or just let me know if you have a question, okay? Don't hesitate to unmute yourself. I'm not really good at watching the chat box. It doesn't look like there are any chats here, but I tend to not pay attention to that. It's much better if you just unmute yourself and say, hey, I have a question, okay? All right.
Yeah,
Yes.
I've got a question real quick.
Okay, thank you.
So let's say you didn't have that graph. How would you solve for the limit if you didn't have the graph?
If you don't have the graph, you really have to look at the table like I did right here. And just kind of pick values around -3, both on the left and on the right, and then see what your output is doing. That's really the only way you can do it without a graph, at least for limits of infinity. And like I said, I just did this one example just to kind of show you what how to do the problem, but we're not going to do that too much. I'm going to keep that at a minimum because you're not, like I said, in the business world, you're not really going to have that application much where you're dealing with infinity. I mean, you might, so I have to mention it, but it's rare, okay? So mostly in your homework, if they give you the graph in almost all the homework problems. They give you the graph. So thank you, that's a good question. Anybody else have a question like that you want to resolve? Okay, so let me see, I want to make sure I covered everything before I move on. Let's look at your homework for just a moment. I'm going to share the screen and we're going to take a look at our homework. This is section R. Just remember when you email me to put section, I'm in section R, that helps me a lot. Seems like it's taking a little while to load there. So can you see the screen okay? Yeah, because it's hard for me to know what you're seeing. You would let me know, right, if you couldn't see the screen. Let's see here. Okay, there we go. So this is the section that we're in, section 1.1. There are only 13 questions, and these questions go pretty quickly when you're answering them, but they are kind of tricky. So let's take a look. So here we have a function, and they're asking, it says use the graph of the function to find the given limit. When necessary, state that the limit does not exist. So here we have the limit as x approaches -5 for our function f of x. Going over to the graph, here's our function. And x is approaching -5. So here's the x-axis. So I locate -5 on the x-axis, and there it is. And as I am on the left, if I pick an x value really close to -5 on the left-hand side, and I go up, there I am at a height of 4, okay? But if I come in on the right-hand side, you'll see, if I go to the function right here, and then over to the y-axis, I'm at a height that is close to 1. So there's a disparity there. On the left, the height is around -5, is close to 4, and on the right, it's close to 1. That means the left-hand limit is equal to 4, and the right-hand limit is equal to 1, as x approaches -5 from either side, respectively. Okay? So it's obvious that there's a break there. The limit does not exist. There's a disparity between the two sides. All right? So the limit itself does not exist. And you'll notice that there's no plus or minus. That means I'm talking about both sides. If you don't see a plus or minus, then you're looking at both sides. So B is the correct answer. Okay, this time we're getting close to -2, but notice this plus sign here that I'm pointing to with my cursor. It is showing me that I'm looking only at the positive side of -2. So when I look at my graph, here is -2 on the x-axis. I'm pointing to that. Now I'm going to go close, not at -2, because if at -2, the function does not exist, right? If you see that open circle there, oh wait, I'm sorry, I misspoke. At -2, the function does exist because I can go up here to this closed-in circle. So the function at -2 is at a height of, it looks like 7 there, okay? But we want to know close to -2. So I'm going to move my cursor just a tiny bit to the right of -2. And then when I draw a vertical line, I hit the graph right about here. And so at the height, we're talking about right around 4, okay? So it's really close to 4 when I go on the right side of -2. I hit the graph and then go over to almost to 4. So the limit on the right side is 4, or on the positive side. Okay, this time we have a function g of x here, and I'm approaching -1, x. So I'm going to look at the x-axis, I'm going to find -1, and I want to focus on the negative side because I'm pointing right now to that little negative that comes after the -1. So when I look at the graph, I'm coming in from the negative side. The function value at -1 is right here. That's at a height of 1. But around close to -1 on the left side here, I come in at a height of 2. So the limit on the left-hand limit is 2. Okay, you kind of get a feel for this. I hope this helps by going through these problems. Okay, so now, oh, I forgot to expand it, I think. But now we have a function and we're looking as x approaches 2 from the positive side. So I'm going to expand this. So here's 2. I'm pointing to the x equal 2. But notice the function here is crossing the x-axis at that point. That means at that point, it's at a level of 0 because y is equal to 0 on the x-axis. So our function happens to be crossing the x-axis at that point. So, and from both sides, it's close to 0. So if you're coming in from the right-hand side, it's going down to 0. And if you're coming in from the left-hand side, it's going up to 0. But they're kind of meeting there at 0. So the limit, not only does the left-hand limit exist, but so does the right-hand limit. And so the limit itself exists, and it's 0. Okay, now this is a limit of infinity here situation. So let's look at the graph. The limit as x approaches -7 of f of x. Okay, so on the x-axis, I find -7, it's right there. And you can see, imagine, now this doesn't show it very well. They really should have had a asymptote drawn there. And this kind of tripped me up when I was doing this problem in an earlier class. It looks like it's touching that line, but it really is not meant to be touching it. And I can't really zoom in here. So this is really a bad picture. But imagine, you can see a divergence here. On the left, it goes off to infinity, and on the right, it goes down to -infinity. So at -7, which is this vertical line here, when x is -7, we're going off to infinity. So the limit does not exist, okay? Remember, infinity can never be reached. And a limit is a constant. You have to be able to say, okay, it's equal to this number. But infinity is just a concept. We can't say equal to infinity, although we write that sometimes just to convey the idea. Okay, so the limit does not exist. And then if we're looking at the function here, they want you to graph it. And by the way, if you get stuck with graphing these, you can do a table of values. Or you can use a graphing calculator. Either if you own one, you can use one, or online. I prefer Desmos.com. So let me just show you Desmos.com real quick. It's really easy to use. What was that function? Hold on. 1 over x minus 4. So f of x, which is y, equals 1 over x minus 4. So there you can see the graph. And what happens is this is a hyperbola is what I meant to say. Hyperbola So you have this split here around 0. But in our particular example, it's been shifted down 4 units. So normally it would be centered around the origin here, but because we subtracted 4 from our 1 over x, it's shifted down here to 0, -4, okay? But it has that divergence going on there. So back to the problem. Here, this graph has been shifted up, and this one was shifted to the left. And these two are shifted down, but this is the correct orientation. You have the positive side, it's above that line of -4, and on the left side, it's below that line of -4, so this is the correct graph. And now it asks us the question, what is the limit as x approaches infinity of our function? So going to look at this graph, x approaching infinity is way out here. And where is the function leveling off? Well, it's leveling off at -4. And remember, limit values are y values, so you're looking at the level that the function is at. So over here, when x is far to the left, it's leveling off at -4. So our limit as x approaches infinity from, it's from the positive side. Well, it's the same thing. If you were going to the positive side, I did the negative side. The positive side also levels off at -4. Okay, so we can say -4 there. And if you were looking at table values for this thing, if I take really big numbers, so if I go off to positive infinity and put really big numbers in here, 1 divided by a huge number is practically 0, and 0 minus 4 is -4. So it's getting close to -4. If you take a really tiny number and subtract 4, you're going to be really close to -4. So that's the limit value. The next question says, what about the limit as x approaches 0? Okay, notice it doesn't tell us which side we're approaching from. So that means we're approaching from both sides. We got to consider that. And when we go back to the graph, if you approach from the left, it's going down to -infinity. And if you approach from the right, approaching 0, right? X equals 0, it goes off to positive infinity. So there you have the limit does not exist because it separates. It's going off in opposite directions on either side. Okay? So that's how you do those problems. Let me do some examples like this. Let me just find a good example here. I had one from earlier. I want to do it. Where is it? Here it is. Okay. So back to the dot cam. Actually, I just realized this example that I want to do is from the next section. So let me talk about 1.2. And I'm going to check my time here really quick. We have quite a few minutes left. When do we get done? At 12:15. Yeah, so we have about 20 minutes, 22 minutes left, something like that. Okay, so let's introduce to you the concept of continuity. And this is coming from section 1.2 now. We finished 1.1, and we're looking at continuity. Okay, so f of x is continuous at x equal a if and only if the limit exists and is equal to some constant and the function value is the same. Let me just give you the layperson's definition. Basically, a function is continuous if you can draw it without lifting your pencil, okay? So remember those pictures that I had earlier? Let's look at those. All right, in example 1, f is continuous. And actually, I think this is the pages that I had from another class because it's all filled out already. Let me go to what we had written up here. I teach this 4 times, okay? So I have 4 sections of calculus, so my notes are all like from, here we go. This is what we did earlier right here in this class. We have a function here, f, And I can draw this without lifting my pencil. So F is continuous. All right. Over here, if I try to draw this function, I have to lift my pencil when I get to this spot right here. I have to lift it up and continue. So it's not continuous. All right, here, same thing. I'm drawing my function, and at this point I have to lift it up, touch this point, and then lift it up again and continue like that. So this is definitely not continuous. Okay, and finally, obviously this is not continuous. Here I'm traveling along, I have to lift my pencil, or my pen if you will, and continue that way. So if you have to lift your pen or pencil, it's not continuous. All right, so it's pretty simple, the idea of continuity. But let me go ahead and give you the official definition. This is actually not the math definition. That's much more technical, and that would be something you would do in a course like Calculus 1. But because this is survey of calculus, we are just kind of skimming the surface on these concepts. And so we kind of use kind of a quasi ways of describing it. So let me give you the definition of continuity. Here we go. Okay, so the first part says that f is continuous at x equal a if and only if the limit as x approaches a of f of x exists and is equal to some constant L. And the second part of the definition is that f of a must equal L. Okay, so continuity requires two conditions. And this definition says if and only if. That means the implication goes in both directions. Okay, so what that means is f is continuous if these two are true, but also if these two are true, then f is continuous. That's what it means to say if and only if. And that's why the implication goes both ways, okay? So if we go back to the pictures that I was showing you earlier, in light of this definition, we have, you can see right here, the definition says that the limit has to exist, okay, and the function value at a has to be the same as the limit. So that's because this point right here, when you plug in a, it's filled in there, right? So you have the limit, but you also have that point equaling L. This is not continuous because, yeah, the limit exists, that's equal to L, but f of a is undefined, it's not equal to L. So that's why we have that disparity there. And same here, yeah, the limit exists, even the function value exists, but they're not equal. And in the definition of continuity, these two values have to be the same. And of course, Here, the limit doesn't even exist, so there's no way it can be continuous, okay? So you have to have the two conditions. You have to have that first, the limit has to exist, it has to equal L, and the function value also has to equal L, okay? Any questions about that? So to kind of explore this idea of continuity a little bit further, let's look at an example. And a good example for discussing continuity is using a function that's defined piecewise. So in this example, I have my function f of x, and it's a function defined piecewise. So we have the top function is 2x minus 3, and that's over the domain when x is greater than or equal to 1. And the bottom function is 4x minus 5, and that's when x is less than 1. Okay, so the question is, these are two linear functions, right? They both have slope. This one has a slope 2, this one has slope 4, and then they have intercepts -3 and -5 respectively. So they're linear functions. That means you can draw a line, right, without lifting your pencil. So independent of each other, outside of the context of this function defined piecewise, they are continuous functions. But you see, we're joining them together. We're restricting the domain. So for this one, x is greater than or equal to 1. And then we're joining it with this one when x is less than 1. Those two lines have to meet at that point, x equal 1. If they don't, then you're not going to be able to draw it without lifting your pencil. So let's just consider that. And I am going to graph this in just a minute, but you don't need a graph to do this problem. Basically, at x equal 1, when we plug in 1 to each of these functions, those y values have to be equal. Okay, so let's try the top one. So first, before I do that, I'm going to label these separately as g of x, just for the purpose of this problem, and h of x. So I can kind of talk about that. Okay, so the top function, g of x, on the domain x greater than or equal to 1, I'm going to plug in 1, okay? And so 2 times 1 minus 3 is equal to -1, right? Because I have 2 minus 3, that's -1. Now, notice that for this particular function h of x, the domain, the value of 1 is not included in there. However, I can plug 1 in just to see where it lines up. So I'm going to do that. Even though h of 1 is undefined, I'm just going to plug in 1. Oops, I was supposed to plug in to h. That's a 4. 4 times 1 minus 5. And I get 4 minus 5, that's -1. So they do line up. So our function f of x is continuous. All right, let's go ahead and take a look at the graph. So I'm going to use Desmos for that purpose. I'm going to let you finish writing here for a minute before I go over to Desmos. And just remember, I am recording this. It may not be the exact recording from your class, but I do post a recording from one of my classes. They're all the same lecture. So it's easier just to post one recording as opposed to posting them all. So, but you get the same material. So I'm going to go and share my screen. And Desmos, I think, I wish this I can make, yeah, there we go. So let me show you how you restrict the domain on a function in Desmos. So my top function is y equals 2x minus 3. But I've restricted the domain. So I'm going to use, I don't know what these are called, but I call them squiggly brackets. I don't know, they just look like squiggly brackets to me. So x is, I type in x, and I want to go down to, see this little button down here that expands your choices. and I want x to be greater than or equal to 1. And then I'm going to close the squiggly brackets there. This, inside these brackets, it's defining the domain. So you can see suddenly I have a piece of the line, right? And now for the next, I just press enter. It takes me to the next line. And then I go y equals 4x minus 5. And I'm going to restrict the domain again. So I'm going to say that x is less than 1 for that piece. And that's the blue line, okay? And they're pieced together. And you can see, like I had predicted, here at 1, the output for both of them is -1, so that they're joined up there, okay, at that spot. So this is a continuous function. And if you want to get a better look at it, you can collapse all these little windows that I have here. So you can use these arrows to collapse. And you can center it by clicking and dragging your mouse to center it. And you can zoom in by scrolling up or down. It'll zoom in and out, okay? And so there's your function. And you can see it's continuous because I can draw it without lifting my pencil, okay? All right, any questions on that one? Okay, going back to the notes, let me look at another example. This comes from your homework. Or this is one like your homework. It asks you to find a value of c so that the function would be continuous. So the way it's worded is find the value. I think in your text or in your homework it says k, it uses k, so I'm going to use k. Find the value of k so that the limit as x approaches 2 of f of x exists, okay? And I can put in a parenthetical note there, and therefore the function is continuous at 2. Okay, so find the value of k so that the limit as x approaches 2 of f of x exists and therefore is continuous at 2. And the function that I'm talking about here is f of x equals 3x plus k minus 2 times x plus 5. And it's this function when x is less than 2. And it's this function when x is greater than or equal to 2. Okay, so in order for this function, again, we have 2 lines here, right? We have the slope times x plus a constant. We don't know the constant. And then we have -2 is the slope times x plus 5 is the intercept. Okay, that's our constant. So again, we have 2 linear functions. And we want to pick our k so that those 2 lines line up at that point x equal 2. So what I'm going to do is I'm going to take 2 and plug it in my top function, and that's going to give me 3 times 2 plus k. I want that to be equal to this number plugged into the bottom function. So minus 2 times 2 plus 5. If these 2 sides or these 2 functions evaluated at 2 are equal, then the function will be continuous, and that's what I'm looking for. What k value will make the function continuous? So I just have to solve this for k. So 3 times 2 is 6, plus k is equal to minus 2 times 2 is 4, plus 5. And I have here, to isolate the k, I'm going to subtract 6 from both sides. Okay, k is equal to 4 plus 5 is 9, minus 6 is 3. And I'm getting a different answer.
Oh, you forgot to put the 4 as
There
negative.
we go. You're right. 2 times 2 is negative, so negative 4. I was going to say, why am I getting a different answer? So negative 4 plus 5 is 1, minus 6 is negative 5. There we go. So that's our K value. And that means that if this function here is 3x minus 5, and this function negative 2x plus 5, then they'll be continuous. If this is some other K value, the two lines will not meet up at 2, and therefore it would not, you would have to lift your pencil, right, to draw it, okay? So there is a problem like that in your homework, and there are quite a few other problems in section 1.2 that I'm going to start. I'll talk about how we find limits algebraically. And this, someone had asked me a question earlier, and I don't think it was in this class. I think it was in another one of my classes. But they were asking me, well, how do you find the limit if you don't have a graph? And you would just plug in the number algebraically to find the limit. So let me look at some examples like that. I need to find my notes. Hold on, got to get my notes. I didn't expect to get this far along because my other classes, I don't know, it went more slowly. So I feel like I'm forgetting something, but we do have quite a bit of time left here. And okay. So when you're evaluating limits algebraically, I'll start out with some simple examples and we'll just get more complex as we go along, okay? Okay, so example 1. The limit as x approaches 9 of the function 32. This is the constant function, okay? And this problem always trips students up, so I wanted to include this as an example. It's so simple, but yet it's just so hard. I don't know why. But let me just kind of, the trick here is you always have to remind yourself that limit values are y values, okay? So in other words, what are y values? Those are function values. And you also have to remind yourself is x is input, y is output, okay? So what this is, here we have the constant function. What is the output of a constant function? It's the constant, right? So the y value in this problem is 32. The x value is 9. So as your input gets closer and closer to 9, your output gets closer and closer to 32. Actually, it doesn't have to get close to 32 because it's always at 32, right? This is a constant function. So if I were to graph this function, here at the height of 32, it's just a horizontal line, right? We did this in our review last week when we were reviewing algebraic concepts. This is the constant function. We can call it y equals 32 or f of x equals 32, however you want to write it. So basically, here at 9, let's say, if x is getting closer and closer to 9, your function values are at 32. So without the help of this graph, you just have to sort out in your mind, remember that limit values are y values, and so 32 is your answer here. Okay? So sometimes I'll have students say, well, is it 9 or 32? So they want to put 9 in there, but because they see x is getting closer and closer to 9. But remember, limit values are y values, so this is your correct limit. Okay, example 2. We have x is approaching -5 and x squared plus 7 is our function. Here's our function. Those are the output. This is the input. Now, what kind of function is this? Well, this is a polynomial, in specifically a quadratic function, so it's a parabola. And I should mention as a note, so in other words, y equals x squared plus 7, or you could say f of x equals x squared plus 7. And all polynomials are continuous. Think about a parabola. So all quadratic functions are parabolas, right? And polynomials, all of them are smooth curves. All polynomials are continuous. So you know that if it's a smooth curve like a parabola or a cubic or quartic, whatever you've got, you're just going to be able to draw it without lifting your pencil, and therefore the limit is going to exist everywhere, and the function value is going to be equal to that limit. So since this is continuous everywhere, I know that my limit value is going to be the same as the function value. So in this example, L equals f of -5 because of that continuity, right? So to find f of -5, I just plug the -5 in, square it, add 7. -5 squared is simply 25, and then when I add 7, I'm going to get 32. Just by coincidence, I got the same answer as the previous problem. I didn't plan it that way. It just was by coincidence. So anyway, 32. Not every answer is going to be 32, just so you know. Okay, see how that works? That's where the continuity comes into play. It helps you, if you know if a function is continuous, then you know the limit value is going to equal the function value. And so that will help you solve the problem. And that's how we find limits algebraically. Okay. Oh, have I gone over time? Wow, I'm having so much fun here. I've gone over time. So I'm going to end here, and I'm going to pick up with examples on Thursday when we start. I'll do some more of these finding limits algebraically. So thank you for joining today, and see you on Thursday.